How does critical state soil mechanics explain liquefaction? Imagine standing on a sandy beach during a storm and feeling the ground suddenly turn soft and unstable. That's similar to what happens during liquefaction in an earthquake. Let's explore how scientists understand this strange behavior of soils using critical state soil mechanics. Soils are made up of tiny solid particles and lots of water filling the gaps between them. Under normal conditions, the solid particles support the weight of structures, and the water just fills the spaces. But when an earthquake hits, it shakes the ground intensely. This shaking causes the soil particles to move and rearrange. Because the water can't drain away quickly, pressure builds up in the pores between particles. This excess pore water pressure pushes the particles apart, weakening the soil's structure. Critical state soil mechanics helps explain this process by introducing the idea of a critical state. This is the point where the soil deforms continuously without changing its volume or the pressure it carries. When the soil reaches this state, it loses its ability to resist shear stress, which is the force trying to slide the soil layers past each other. Instead of acting like a solid, the soil behaves more like a thick liquid. Scientists use models like NorSand to understand how soils reach this critical state. These models show a flow liquefaction surface in stress space. When the stress path of the soil during shaking crosses this surface, the soil becomes unstable. It then suddenly loses strength and starts to flow, causing the ground to behave like a fluid. This is what we see during liquefaction, where the ground can no longer support buildings or roads. The process of liquefaction can be broken into stages. First, the shaking causes excess pore water pressure to build up, pushing the soil toward the flow liquefaction surface. Once it crosses this boundary, the soil quickly loses its strength and deforms a lot. The soil then reaches a steady state where it keeps deforming at a constant rate, with very little shear strength left. This understanding also explains cyclic mobility, where repeated shaking causes the soil to become softer over time. It might not fully liquefy, but it can become more prone to failure. Knowing this helps engineers predict where ground failure might happen during earthquakes. They can design foundations and earthworks to resist liquefaction by improving soil density or adding drainage systems. In the end, critical state soil mechanics provides a clear picture of how and why soils turn into a flowing mass during earthquakes. It helps us prepare better, reduce damage, and keep communities safer when natural disasters strike.